Get started? Okay. Okay, so what have we done so far? I've told you what a subfactor was, and I told you that to understand them, we're going to look at their representation theory. There's the gadget called the standard invariant, and then we gave an alternative axiomatization of this thing called the standard invariant. First of all, we talked about it as a pivotal unitary two-category with some one or two more constraints, and we saw that we could instead organize that as a planar algebra. And then I gave you some sense of some of the tools that we use to think about planar algebras. So this afternoon, the point is to actually prove the theorems, that is, explain exactly what subfactors there are out there in certain index ranges, and to indicate how we both prove there's nothing else and construct those examples there. So before we do that, just sort of some questions about what we're doing. I just want to say, why only the small examples? And of course, the answer is that the big ones are too hard. And so I just want to indicate a little bit about what goes wrong. So first of all, this case that we talked about before, the fixed points under some group sitting inside the hyperfinite 2-1 factor, well, this shows that the problem contains classifying finite groups. So that's sort of a bad idea. That's hard. That's sort of, we're going to need to limit ourselves in some ways. And another rather different thing that causes us to worry is that the planar algebra is not generally a complete invariant of the subfactor. Now, although I told you earlier how you extract a planar algebra from a subfactor, I didn't actually ever talk about the reverse process of trying to reconstruct the subfactor. Fortunately, it's actually really quite easy. You can just take A to be the limit of these Pn plus spaces. Is this the way? Yeah. Okay. Where here the inclusion between Pn plus and Pn plus 1 that we're taking this limit along is just this map of adding another strand on the right. Okay, that tangles a map from Pn to Pn plus 1, and so we can just take a limit, all the algebras including into each other, and then we can take B. Sorry, I've got my letters the wrong way. I'm telling you the subalgebra now. We can also take the limit of the Pn minuses in the same way. And what's the inclusion here? Well, you can include Pn minus into Pn plus this way by adding a single strand on the left. Okay, and so that gives us some tower of algebras we're taking a limit of, and some sub-tower of algebras that we're also taking a limit of. And you might hope that this simple recipe recovers the subfactor you started with. And this works in some cases. This recovers the subfactor if it's hyperfinite, but generally not otherwise. And otherwise, generally, you're really losing information, dropping down to the planar algebra from a subfactor. And this effect first kicks in at, well, we're actually not exactly sure where it kicks in, but it kicks in somewhere between 3 plus square root 5 and 6. So we know this isn't an issue below 3 plus square root 5, it's definitely an issue from 6 and above. So that starts to become an issue. Of course, from our point of view, the standard invariant is the interesting thing anyway. That 2 category that we're trying to understand is interesting. Who cares if you can't reconstruct the subfactor from it? What were subfactors for anyway? Okay, so given that we face a few different problems for really understanding all subfactors, and we're going to look at small ones, the next question to think about is what should small mean? And I'm not really going to justify the choice of small that we've made in this project because somehow from the subfactor point of view it was obvious that index is the thing that you're meant to care about. I admit it's actually not that natural from some other perspectives. So I just want to tell you what the other perspectives are that you might think about. So one option is the rank. So that's the number of simple bimodules. So you might try and think about pivotal 2 categories with very few simple objects. And some good work has been done in that direction, but the number ends up being very small, like 2, 3. Another thing that's very interesting that I think it would be possible to make a huge amount of progress on, that hasn't been done, is understanding pivotal categories or pivotal 2 categories with small global dimension. So this is the sum over, say, just look at the n objects of the squares of the dimensions. So you just take the sum over simple objects, square their dimensions. So in the group-like cases that we had over here, this global dimension is actually the size of the group that you are looking at. And so that's a reasonable number that tells you a lot about the category, and no one's really done much thinking about pivotal categories of small global dimension. And then finally, there's the thing that we're looking at. We're looking at small index, which means well, it's the dimension squared for some object. So that is, you should think that we're thinking about pivotal categories which happen to contain at least one object whose dimension is quite small. Okay, and that's the sense that we're filtering by. But it's, I think, good to remember there are other possibilities out there. Okay. Maybe one more sort of instance of how things go wrong, even in the small examples, focusing on index. It turns out that how to say it? Well, you can make subfactors of the following form. So remember, given the hyperfinite 2-on factor, you can make any finite group you like act on it. So here's fixed points under Z12, and here's sort of the semi-direct product with some action of Z13. You can actually make a different subfactor that looks like this. So you're using different actions for each quotient of PSL2Z, which is basically every group you've ever heard of in the history of the world. And these things are all index 6, but there's a huge jungle of them. And so somehow easy but unmanageable problems in group theory sort of descend into classifying subfactors even in relatively small indices. And this is index 6. Okay, but if you remember, the theorem that I wanted to tell you about today was only out to index 5, where none of these things have yet become a problem. So let me state a series of, I guess, 3 theorems, 2 historical ones, and then the one we're going to prove this afternoon, more or less, telling you what sort of thing is out there. So this one is essentially due to Adrian Ochianu at Penn State, who has discovered many, many, many wonderful things about subfactors and published very few of them. All subfactors with index less than 4 have principal graph. And one of the ADE Dinkin diagrams. Array for ADE classifications. Moreover, there are the following numbers of them. Well, for each AN, there's exactly one subfactor with that principal graph. And in fact, these were those Templey-Lieb planar algebras at roots of unity, the things that realized these guys. We didn't quite spend enough time talking about Templey-Lieb to see that the principal graph was really AN. For the D2Ns, there's one of each of those. I realize there's a typo in my notes if anyone's following along. I got this table wrong. For each of the odd Dinkin diagrams, there are none. And then there are two subfactors of the principal graph E6, none with E7, oops, sorry, two, and two with principal graph E8. And all of these guys are actually relatively simply understood as sort of coming from these really boring AN examples that are just temporarily. If I had an extra hour, I would probably spend it on showing you all those examples in detail, because they're very helpful. Happily, actually, there are nice papers about all of these examples that are written very accessibly. There's one paper by me and some other people on the D2Ns, and some papers by Stephen Bigelow about E6 and E8, which are a great place to start learning about all this stuff if you want to hear a bit of paper about it all. Okay. And so then there's a theorem essentially due to Popper, but a lot of other people contributed, so I think Popper and others. And at index 4, so we have a very, very similar result. All subfactors have affine Dinkin diagram principal graphs. Again, you can say exactly how many there are of everything. Let's write these out. Yeah, thank you. Yeah, strictly less than 4. Yes. So at index 4 is the first place where you see infinite principal graphs appearing. Everything else that's appeared up here is some finite principal graph, finitely many simple objects. But here, it's a little bit more complicated. There's a lot of these first guys. And in fact, you can actually very explicitly say what all of these things are. These are all realized as twisted G-graded vector spaces. So here, G is a finite subgroup of SU2. And omega is some 3 cocycle on that group, and the different choices of this omega is what's controlling the different instances here. So this thing here is actually just some tensor category that I've told you, and you might wonder a little bit about what's going on, because the standard invariant of a subfactor is meant to be this 2 category with 2 objects. Well, in all of these instances, there's this Z mod 2 grading on this gadget, and if you kind of split apart the grading into 2 different objects, you can, a Z mod 2 graded tensor category you can pretty much think of as a 2 category with 2 objects, and that's what's going on here. All of these examples are actually very, very simple things, just G-graded vector spaces with the associativity twisted by a 3 cosine. So the story there is pretty simple. And so what do we say above 4? So this is this theorem is sort of something that you can put together out of a whole lot of papers by a bunch of people. There's a series of 4 papers called Subfactors with index less than 5, or something like that, parts 1 through 4. But there's also another half dozen papers that sort of were specifically written in order to give this classification. There are a lot of different co-authors on all of them, and I encourage you to look at the survey paper to see who should actually get credit for everything. It's certainly not just mine. Okay, so we need to be a little bit more technical here to state a theorem. So I'm going to put some adjective, an extremal subfactor. It turns out extremal doesn't matter very much. So there's a dichotomy. So first of all, there's one possibility. It either has either the principal graph is A infinity, and it turns out this is a possibility at all indexes above 4, but it's kind of boring. And the standard invariant is just temporally leave. So the planar algebra is just spaghetti, no interesting stuff. Or is one of the following 10 cases. So these things have names, essentially named after the people who first discovered them or conjectured that they existed. There's this thing called Hagerup subfactor. I'll draw its principal graph. This was actually mentioned a little bit earlier before lunch. So remember the principal graph comes in 2 components. So I'm going to actually draw both components now. Index that crazy number. There's the extremely poorly named extended Hagerup subfactor. Which gets its name because the principal graph is almost the same, just longer. And, well, maybe I'm, well, and there's another principal graph there. I'll be drawing. With index. It's actually hard to write down the index. I mean, you need to go to some quite high degree extinction of the rationals before you get to write it down, and it takes up too much blackboard space. But it's some number, ever so slightly higher than that one. The Seda Hagerup subfactor. And its dual principal graph with index 5 plus root 17 over 2. And then 2 more. These other 2 are actually much less mysterious than those first 3. And if you look at the notes on my webpage corresponding to parts of this morning that I didn't get to, you can actually describe how these sort of fit in families. And so they're just low index instances of things we do understand pretty well. Sorry, I'm mixing up my graphs. So these graphs are named extremely unimaginatively. These graphs are trees, and then the name here is just the length of the branches of the tree. might wonder if this guy at 5 plus root 13 over 2, this one at 5 plus root 17 over 2, and this one at 5 plus root 21 over 2 sit in some sort of family, and they don't. So I think that's just a numerological accident of small numbers in small number fields. Yeah, okay, so I only drew 5 cases, but I said there were 10. So let me just say, along with duals or complex conjugates. So each of these things I've indicated on the board actually lives in a pair of non-isomorphic subfactors that are extremely closely related to each other. The first 3 are not equal to their dual, which basically just means that the objects A and B in the 2 category are not, there's not a symmetry permuting those. These guys are self-dual, the objects A and B are completely symmetric, but there's a complex conjugation on these things which gives you slightly different gadgets. And that gives you the 10. Okay, so I'm not sure whether a statement of a theorem like that makes you depressed that it's just some random pile of rubbish that you get out at the end, or excited that that there's so few possibilities, even though we started with this very abstract-looking description of what we were after, and we discovered these beautiful jewels sitting on the beach as we walked along. I'm in the latter category, but you're free to feel that this is also just a pile of random junk that comes out. So what are we going to do to prove a theorem like this? So here's the sort of the outline. Is to do some combinatorial work to enumerate potential principal graphs. We're going to sort of show that if you're the principal graph of a subfactor in this range, you've got to lie in one of some families, something, something. Then we're going to stare at those families, and we're going to eliminate as many as possible. Or as many as possible means until we run out of energy, fail to eliminate things. Eliminate as many as possible using either combinatorial or number theoretic obstructions. And then finally, when we've run out of ideas on how to eliminate any more graphs, we decide, well, maybe these things really are the graphs of subfactors that exist, and we go and directly somehow classify the planar algebras with the remaining principal graphs. And this description really does actually work in the sense that by the time you're done with step 2, all that's possible are these 5 particular graphs. And by the time you need to actually classify things with a given graph, every case you're looking at has exactly one instance realizing that graph, which is, I think, perhaps somewhat surprising that combinatorial and number theoretic results are so powerful. Okay, so there's going to be a bit of a lengthy period here where we talk about combinatorial aspects of principal graphs and how one might enumerate them. So let's think about what we know about principal graphs so far. Well, the main thing that gets us off the ground is that the index of the subfactor can be read off from the principal graph. It's the square of the norm of the adjacency matrix. And so since we're only interested up to 5, we're only just looking at graphs whose adjacency matrix has relatively low eigenvalues. So it will maybe take a moment to get to the point of describing how we get these results, but let me tell you what the results are going to look like. We're going to have two types of families of graphs. One family is going to one type of family is going to be called a vine. The other one is going to be called a weed. So a vine represents all graphs obtained by called translating a fixed graph. I'll draw you a picture to indicate what that means. So here's a vine. And always through here, there's actually kind of a pair of graphs because the principal graph has two components, but I'm often going to be lazy and just draw one. And here I've drawn one of the vertices as open. Well, what I mean is that when we translate, we can just tack on some longer chain of edges there. So this family is everything you get from taking this graph and just extending, in fact, extending by an even amount that initial chain of edges. Okay? So these are very simple sort of one-parameter families of graphs. That's what I mean by a vine. It's very important that you translate by even amounts because the vertices at odd and even depths mean very different things when you go. Remember the category theory for a moment. And I should also say that here we're always having in mind these graphs are sort of decorated with all the information about which objects are dual to which other objects. And that's part of the data of a family of principal graphs. Okay. Then the other sort of family that we're going to have are these weeds, because they're much more annoying. Weeds would represent all graphs obtained by translating or extending a given graph. Now, extending is a much more complicated operation than translating. So let me just put an example again. So here, I'm going to draw this guy with some open circles on the right as well to indicate that I can make modifications on the right side as well. So another thing that might appear in this family is anything you can get by increasing the initial chain. Remember initial here, that leftmost vertex is always the identity morphism in the two category. So that's the special vertex. But then on the right, you can do whatever you like. You can add more vertices at strictly higher depths than the greatest depth of the fixed graph in any way you like. Okay? Maybe keep going. That might be an instance of another graph represented by the weed corresponding to this fixed graph. We can add on arbitrarily complicated stuff at strictly higher depths than the greatest depth that appeared here. Or we can extend the initial one. Okay? So these are big, messy, infinite families. It's basically just saying that if you truncate it at a certain depth and modulo this translation issue, they all start like some particular thing. Okay. So one thing to observe just there is clearly the weed, just a single edge, open at both ends, represents all possible principal graphs. Okay, because remember this object here was always 1, and the first object, the first depth was x, our generating one morphism, and now we're allowed to do anything we like. So all graphs look like that. So the idea is that we're going to have a sort of engine for taking results about possible principal graphs and making them better. So we need the idea of a classification statement. And we're going to have a machine that takes classification statements and turns them into new ones. So what does this look like? So this says every subfactor with index at most L whose principal graph is a translated extension of gamma naught, that guy there, is represented by some phi in V or some weed in W. Okay? And so to sort of bootstrap this statement here, that this weed clearly represents every possible principal graph, we can get started by saying, well, if you're interested in any old subfactor, whatever principal graph whatsoever, up to any limit, well, that's always represented by that same weed, okay? I mean, you can always actually just put any gamma naught there as long as you put the same gamma naught in the pile of weeds, and that classification statement is trivial. But, well, this is some extremely boring classification statement about the principal graphs of all possible subfactors. And we're now going to work out how to improve a classification statement. So this is sort of the meta theorem. So let's just take theorems like that and produce new ones. So here, some classification statement. Well, it implies, sorry, let me write that slightly differently. So in that set of weeds here, let's point out that there's one particular one there called B. B is for bad. We don't like it. Well, that classification statement there always implies some other classification statement. The same gamma naught, the same L, the same V, but with B tacked on, so moving B from a weed, which is a disaster, to a vine, which is maybe not so bad, at the expense of adding some new collection of weeds, where here, WB consists of all one-step extensions. So that means we've just taken the graph W and added a few new vertices at just the very next depth, but only one more depth. Consists of all one-step extensions of W staying below index L. Okay? So all this is saying is that if you are some translated extension of B, then either you're just a translation of it, okay, in which case this B thought of as a vine takes care of it, or you are a non-trivially extended translation of it, in which case one of these one-step extensions of W takes care of it. Okay, so this is a very easy fact. And then the great observation is that WB is always a finite set. And better than that, it's a finite set which you can quite efficiently write out. So why is it a finite set? Well, the lemma here is that if you've got one principal graph and it's a subgraph of another one, then let's say it's sort of strictly a subgraph, we've really added something, then the norm of gamma is really strictly less than the norm of gamma prime. Okay, so if you take some graph and you add new stuff to it, the norm is really going up. This actually doesn't require that much thought. This norm is just the size of the largest eigenvalue. You can use the corresponding eigenvector for gamma as a sort of test eigenvector for gamma prime and use that to use this lower bound. Okay, so certainly as we grow things, the norms are only increasing. But then the other thing to say is that adding finite number of edges at a single depth, increases the norm without bound. Essentially just because if in your entire graph you have anywhere in it a single vertex of high valence, this norm of the graph is at least the square root of that valence. And so if you're trying to think about graphs that stay below some norm limit, there's just some limit to the number of new edges you can add in the next depth before you push some vertex up to too high a valence, and the norm becomes greater than the snapper value. So that's the proof of this observation, that these one-step extensions are actually finite sets. Thank you. Without bound, yeah. I mean, maybe this was a silly way to say it. I mean, just having, or what I really should have said is if you have an invalent vertex anywhere in the graph, your norm is at least the square root n, and that then directly contributes back to it. If you added too many edges at the next depth, one of those vertices, so if I'm thinking, I've got my graph fixed up to here and I'm adding some number of edges out in the next depth, if I had too many edges, by the pigeonhole principle, at least one of these vertices now has too many edges on it, so it pushes the norm up too high. Okay, and you can actually see that it's relatively easy to enumerate this set. You just kind of treat the number of edges in each of these positions sort of as the digits of an odometer. You keep on clicking them up until you push over the norm limit, and then you go back and push that one back to 0 and start increasing the next one as well. It turns out there's actually a huge amount of really kind of cool combinatorics in doing this very efficiently. And we've sort of got out to the regime. This theorem is not so bad. It takes a couple of seconds of computer time doing this sort of stuff to do it. But going out to 6, we're actually kind of trying to do this very efficiently. And there's actually a grad student in the computer science department at ANU who's writing really fancy programs to do this really nicely. Okay, so this is the theorem. Now, the reason why this is a good theorem is that basically whenever you see a weed that you don't like, that you can't deal with, you can't understand the principal graphs represented by it, you can kick it out. The cost of kicking it out is that you get a bunch of new weeds in your classification statement, possibly many new weeds, but you know more about them because the graph is now specified out to a larger depth. So you have a hopefully strictly better chance of understanding the subfactors with these principal graphs because you've learned more information about them. But there's a trade-off. You want to run this theorem sufficiently far that there are no weeds that you have no handle on, but you don't want to run it too far that there's just ridiculously many weeds that you can't cope. Now, in some cases, you can actually get really lucky. There's no reason why this set of weeds here couldn't just be empty. Okay? Once we're up close to the norm limit, as you add more edges, there might just be no graphs to fit in here. And an initial version of this theorem that was proved up to 3 plus square root 3, which is in between 4 and 5, was able to be proved exactly because of that sort of lucky situation. You apply this meta theorem over and over again, and you end up with a classification statement with only vines to deal with. And somehow that's a lot easier. So when you're not lucky, you need to know when to stop. Like other aspects of life. And so I'm just going to tell you the place that we stopped using this sort of combinatorial argument at. But it took a lot of effort choosing this particular place to stop. Basically, we were sort of reverse engineering by seeing what we could actually deal with and trying to choose a stopping place that sort of corresponded to our abilities. Okay, so here's the classification statement. So in the set of vines, there's some rather large set of vines. We had 43 of them in here, and some of them are pretty ugly. This is an actual example. the sort of complexity of the things in that set of vines. But there's an interesting story about vines still to be told, which means you shouldn't worry too much about the things there. And then just 5 weeds, which I've said this in, there's one more ingredient in reaching this that I haven't actually admitted to yet, but I'll say that. Yes, they do, because I haven't picked up the red pen yet and shown you the dual data. Yeah. Remember that we're running along with the dual data all through here. And the missing ingredient in getting to this result is also related to the dual data. Yes, I've forgotten how complicated these are. Okay, and of course, these ones are all weeds here, so really these circles at the end are all open circles where you can still add more stuff onto the right. Let me quickly add some dual data. These cases differ. In this case, those guys are dual to each other, whereas in this case, they're self-dual, like that, somewhat crazily like that, like that. Okay. But essentially, it's just combinatorics getting up to that point. The thing that I lied about, or that I neglected to tell you in describing this, is that there's a very important condition on a pair of principal graphs, which we're using along the way here. And let me just slip it in here. So recall that, so here, x is our favorite object, the thing where tensoring with x tells you about the edges in this graph. Recall, of course, that x tensor z tensor x for any z is isomorphic to x tensor z tensor x. Okay? Now, what is this principal graph recording? The principal graph is recording all of the combinatorics of tensoring on the right with this fixed object x, or this fixed one morphism x. It's showing you how z tensor x decomposes into simple one morphisms again. But because we've recorded the dual data all through here, we also know how to compute tensoring on the left, just because x tensor z is, what is it? It's z dual tensor on the right with x, all duals. Okay? So if you know how to tensor on the right with x, the combinatorics of tensoring on the right with x, and you know the combinatorics of dual, you also know tensoring on the left. And so this just becomes some combinatorial equation telling you that this is basically saying if you start at some vertex z and then follow an edge, and then follow a duality, and then follow another edge, that's got to be the same thing as taking duals, following an edge, following a duality, and following an edge. And that's some combinatorial constraint on these graphs. And what I neglected to say is that we're using that all along the way in this sort of that meta theorem. We compute this set WB of new weeds, and then we check this condition, which is just a sort of local combinatorial condition about paths on the graph. And if we didn't do that, then we'd never get anywhere. Okay, so at this point we sort of bifurcated to 2 separate classes of problems, sort of dealing with vines and dealing with weeds. And roughly the answer is that there's now beautiful machinery that deals with all vines all at once, no matter what. But that every weed ends up needing a separate paper written about it, which is kind of a pain. So let me tell you the nice uniform story about vines, first of all. So this story is sort of an interesting one in that we're suddenly going to import a whole lot of number theory into the problem. And this number theory we only realized could be imported into the problem after the subfactor planar algebra perspectives and the fusion category perspectives had sort of both been, well, we'd realized they were the same thing. Because this number theory was stuff that people working on fusion categories and modular categories worked out, and we just borrowed. So it turns out that in a modular category, whatever that is, we won't quite go there, there's this thing called the S matrix, and the entries of the S matrix cyclotomic integers. Okay, sums of roots of integers. And then Eddinghoff and Nikšić and Ostrich realized that you could use this to show that every dimension of an object in a fusion category is also a cyclotomic integer. But it's absolutely essential here that the category is fusion, that there are finitely many symbols. Without that finiteness condition, you've got no hope of anything like this being true. And so in particular, notice that all of these principal graphs corresponding to divines really do have finitely many objects. These guys could be infinite, because we might add infinitely many vertices onto the right to get our principal graph. But these guys are definitely finite. And so in particular, the index of a finite depth subfactor is cyclotomic. And this was a giant surprise when subfactor people first heard about this, because no one had really expected there to be much number theory in studying these things. So the first thing that got done here is Seda and Yasuda showed that for one particular vine, this one that the Hagerup subfactor and the extended Hagerup subfactor came from, so some arbitrary length chain and then two arms of three edges, has only two cyclotomic translations. That is, translations of that graph where the square of the graph norm is a cyclotomic integer. And those were translating it by nothing at all, or translating it by 4, which I guess it's gone by now, but those are exactly two of the cases that show up in the theorem. And this was by a kind of intense piece of 19th century number theory. And for a while, I mean, and this was sort of an entire paper in CMP doing sort of just this one graph, showing this result. But what we eventually realized with Frank Caligari and Noah Snyder, that for any vine, something that looks like this, some initial chain of edges of arbitrary length, and then some fixed thing out in the end, this blob, there's a little dichotomy. Either gamma n is just an or dn, or there's an effective constant. Oops. Really compute. So this indexing here, that n there is meant to indicate that we're looking at the one with n vertices total. Okay? So gamma n does not have cyclotomic index for n greater than this. Okay? In particular, this is just saying that for any vine, there's at most finitely many cases where the index is cyclotomic, and the bound you need is explicitly computable. It turns out that this bound tends to be explicitly computable and absolutely gigantic. There's a slightly stronger result than this one. Not only is the index of the finite depth subfactor cyclotomic, but all of the multiplicity-free eigenvalues of the adjacency matrix have to be cyclotomic too. And there's another version of this theorem with a far better constant that says that after that constant, there is some multiplicity-free eigenvalue of the adjacency matrix, which isn't cyclotomic. So you actually use a slightly different theorem in practice. But this is the idea. You compute this n, you go and check the finitely many cases in that vine. In practice, you find that basically none of them have cyclotomic indices anyway, and then after some finite point, you know about the number theory, you just don't have to do anything anymore. And yeah, so that somehow is just a hammer that deals with vines. And we sort of got very lucky. I mean, we sort of had already got to the point in understanding this that we knew that any sort of theorem would involve analyzing a huge number of vines, and we were sort of, well, I guess, getting ready to give up because there were too many. And then we sort of got lucky and realized there's a really general purpose way to deal with the problem. Okay, and in practice what happens now is that anything that survives this test, you strongly suspect really is the principal graph of some subfactor. Okay. So still to prove this theorem, we've got these 5 crazy weeds that we need to be able to understand. And to understand weeds, we're going to need a little bit more theory about planar algebras and 2 categories. And this is so I need to say a little bit about what a connection is, which is something that was introduced in the subfactor literature as sort of a well. So you might know about 6J symbols for tensor categories, and sort of the general idea that you can sort of exhibit a tensor category by writing down all these 6J symbols satisfying the pentagon equations, but that in practice it's a total disaster. And the idea of connections is to sort of extract an easier problem, where you don't get a guarantee that you've really defined a tensor category at the end of the day, but there's much less to check. And in practice, when you have a connection, you really do have a tensor category. Close enough. Okay, so let's talk about connections for a little. Okay. So given a principal graph with all that dual data, there's something even fancier than that graph planar algebra we talked about, called a 2-sided graph planar algebra. So this is not a planar algebra in the sense that we had before. We're going to need to sort of extend the axioms a little bit. So in this sort of planar algebra, there are 2 types of strings that are allowed, which which I'll try and actually do in different colors. They're sort of I like to call them, give the names Dexter and Sinister, because there's something left and right about them, and one of them is better than the other one. And so there are vector spaces for this fancy sort of planar algebra, p subscript omega. For omega, a word in Dexter and Sinister. And what is this vector space? Well, this vector space is the collection of all loops on the following graph. So here I'm going to write the AA objects as my two category. Here I'm going to write the AB objects. Here the BB objects, and here the BA objects. Okay, and so I'm going to have a bunch of vertices sitting in the four corners of a square, corresponding to all those objects, and I'm going to draw a bunch of edges between them. So these edges here are going to correspond with tensoring on the right with my favorite object x. Here they're going to be tensoring on the left with x dual. Here they're going to be tensoring on the right with x. And here they're going to be tensoring on the left with x dual again. Okay? So that's some big graph that sort of sits over a square. And the point is...
Definition of a particular example of a two-sided graph planar algebra, not definition of what a two-sided graph planar algebra is.
No, this is a definition of what so for each principal graph with dual data, I'm defining the two-sided graph planar algebra associated to that data. Yeah, I mean, you could imagine talking about two-sided planar algebras where there are two string types and formalizing those. And you could do that if you wanted to, and then this would be an instance of it. But there's only one two-sided graph planar algebra for each graph.
So do you have a two-sided graph planar algebra? Do you have a series of vector spaces which are indexed by?
Yeah. So for each word in D and S, there's some vector space here, and now I'm defining what that vector space is.
Do you need a plus and a minus?
That's a good question. Do I need pluses and minuses? Yeah, okay. So I've sort of glommed the plus and minuses together here. So I haven't quite told you about these loops. Let me just finish saying one more thing about the loops, and then I'll tell you how the pluses and minuses comes in. So, so that over each D step, we follow a horizontal edge. And over each S step, we follow a vertical edge. So you've got some word, and that word tells you to look at particular types of loops on this graph. As you read along that word, anytime you are at a dexter step, you've got to follow a horizontal edge corresponding to tensoring on the right with x. And anytime you're at an S step, you've got to follow a vertical edge of this graph corresponding to a tensoring on the left or something. Now the pluses and minuses just come in with where, in fact, there are really actually, there's two signs. There's two pluses and minuses going on. This loop could be, the base point of the loop could be here or here or here or here. And that sort of divides these loops up into, this vector space up into four different pieces which actually don't interact. And that corresponds to the plus and minus pieces in the earlier planar algebras.
So does that correspond to strings where everything's a D and everything's an S?
Yes. The original graph planar algebra is exactly the subset where you only take Ds, and so that means you're just walking back and forth here, and the plus and minuses are loop spaced here versus loop spaced here. Yes. Okay, and I'll cheat horribly here and just say same action of planar tangles. As for the graph planar algebra. That is, you take this state sum of factors to do with critical points in the planar tangles, and you can find in various papers a careful description of what that actually is. Okay, so given that little combinatorial gadget, the two-sided graph planar algebra, we can say what a connection is. A connection is just an element in a particular one of these spaces. It's an element C in P, SD, SD. Okay? And then we say connection is bi-invertible if there exists some element C inverse in P, ds, ds, So the two equations hold. I promised I'd use different strings here. Which way is it going? There's an S string. There's a D string. So that's some equation which holds in the graph planar algebra, and similarly, similar to that. Okay, so that's some particular type of element in the graph planar algebra. And finally, there's a gauge group. This is sort of setting up to a theorem. Sorry, maybe I should have said the theorem first before giving all these definitions. So what is this gauge group? Well, there's actually two gauge groups, a GS and a GD. And the big one is the product of the two. What is this? It's a product of groups over. Sorry, this is a little bit silly. Let me not write down what it is. What does the gauge group do? It basically, if you see two vertices here and here, and you see there are n edges between them, there's just the unitary group in n dimensions acting on loops that pass through that bundle of n edges by basically sort of permuting those edges around. Okay, so you can, if you imagine you just picked some single edge here between two vertices, there's just going to be a copy of U1 acting on any loop that passes through that edge by multiplying by that scalar in U1. Okay, if there were a pair of edges, maybe the gauge group might have an element in it that swapped those two edges as an element of U2. So there's some big group here acting on the space of linear combinations of loops, so in particular on this whole graph planar algebra. But the nice thing about how it's set up, so let me not say all of that, the point is that there's this gauge group acting on the two-sided graph planar algebra. But the important thing is that it's set up in a way that it preserves by unitary connections. Okay. Whew. Okay, sorry, lots and lots of machinery. What's the amazing theorem? Well, given a connection, we can define what's called the flat subalgebra with respect to that connection. And so this is some subalgebra of this giant graph planar algebra. So this is some planar algebra, and the space Fn plus consists of all those linear combination of loops in this DDDDD space of the graph planar algebra. Here there's, I guess, 2n copies of D, such that there exists a Y in PSSSSS, so that the following thing works. We've got our X, imagine all of its strings pointing up there, and then we draw a line going behind all of these, where each of those little crossings there is a copy of this connection C that we're fixing. And we ask that this equation holds, basically that you can pull through that copy of the red line with all those connections sitting there and get this picture here. Okay, so here's some strange thing you can do given a connection. And these properties here easily ensure that this thing we've defined here is actually a subplanar algebra. If you take two things satisfying this, you can compose them in planar ways and get another thing. satisfying that condition. And
Sorry.
Yeah.
How do you use the C to define this?
Yeah, sorry. All of those crossings there
Oh.
are copies of C. I mean, these relations are sort of saying it acts a little bit like a crossing. They're randomized to two moves. Okay. And so gauge equivalent connections, in fact, give equivalent flat algebras. And then the sort of surprising thing is that this is really the way to build all planar algebras in some sense. That is, if you give me some planar algebra with some specified principal graph, I can show you a recipe for producing a connection in the corresponding graph planar algebra so that the flat algebra recovers the planar algebra you started with. And again, this is, I think, something that's kind of neat and amazing about pivotal two categories, and I think it would be really fun to see how far it can be generalized in other directions. So let's just say that again. So given P, planar algebra, principal graph gamma, there exists a connection C in the graph planar algebra. Sorry, there's two-sided graph planar algebra for gamma. And in fact, it's kind of easy to write down what this connection is. I mean, it's just some collection of 6J symbols. Maybe look at the notes if you want to see the formula. And the flat algebra is P again. Okay, so this sort of schematic picture that you should have is if you look at this set of all connections for some fixed graph gamma, well, we can start with a planar algebra with principal graph gamma, and from that we can produce a connection. Now, if we use that connection to come back again, we get back the planar algebra we started with. But in general, not all connections on gamma actually give you planar algebras with principal graph gamma. You can fall out into this bigger class here of planar algebras, but with an important restriction. Even if you don't get the right planar algebra again, you always get exactly the right index. So any connection on a graph of that of some particular norm gives you a planar algebra by taking flat stuff with exactly the index you were hoping for. Okay, so that's a huge piece of machinery that this works. But what's the idea now? Well, one way that you can show that a planar algebra with a given principal graph doesn't exist is by analyzing all of the possible connections on that graph, and either showing, if you're lucky, that there are just no connections on that graph, which is actually surprisingly common, or identifying those connections that there are on that graph and showing you that they all give planar algebras with the right index, but the wrong principal graph. And nearly always what happens is that when you find sort of spurious connections over here, they give you, the planar algebra they give you back is just the boring temporally planar algebra at that specified index. And I think we know very, very few cases where you sort of start, where you look for connections, aiming for some graph, and get some different but still interesting graph. Okay. So, let me give you an example of the sort of things that you can prove using that. Yeah. Oh yeah, sorry, I didn't look at the time at all. Yes, thank you. Done.